All right, so any questions? Yeah.
So I was just curious how to do number 30 first, like I want to know.
Number 30.
Yeah, it's from the like the supplementary ones you had a note to do.
Oh, yeah. All right, let's see. So we're still in chapter 3, right? So supplementary exercises, number 30. Oh, yeah, mathematical induction. Well, let's see. Let's just look at part B. So let's prove the sum from I equals 1 to n of some constant times whatever a sub I is the same as pulling that constant outside and summing the a sub i's. And you did a less formal version of this in another homework set, right? So, and this is for n bigger than or equal to 1. So what's the idea here? We believe this is true, right? And if I give you a particular value of n, say n equals 3, what is this saying? This is saying c times a1 plus c times a2 plus c times a3, this is what we're asked to prove, equals c times a1 plus a2 plus a3, right? That's what we're asked to prove for n equals 3. And that's clearly true, right? Because we know we can factor a c out of that left-hand expression, and we get the right-hand expression. But to prove this for all n, we have to do something like this. And we have to factor the c out of this expression that has this mysterious dot, dot, dot in the middle. And that's where somebody who's being a troublemaker is going to raise an objection and say, wait, how do you know that, that dot, dot, dot and that dot, dot, dot work this way, right? If you have actual terms, c times a1, c times a2, c times a3, we can pull out the c and we can multiply c by each of these and confirm that we get that. But when we have these dot, dot, dots, we can't do that, okay? We can't just take a rule of arithmetic or mathematics that works in some cases and then say dot, dot, dot and expect it to work in those cases, okay? To make such a claim, that's what we use mathematical induction for. So with that, the challenge is the following. There's mechanics of, stating a proposition and all that kind of stuff, doing a base case. But here's the essence of the inductive step. Given c times a1 plus c times a2 plus up to c times an equals all of this. All right, prove that if we go up to n plus 1, we still get this equality. So we want to prove that that equals c times all of this. If we can make that inductive leap, then we can wrap it into the formalism of a mathematical induction proof, and we're done. So how can we bridge the gap from what we're given to what we're trying to prove? And the basic idea is we know this is equal to this. So let's just add c times an plus 1 to both sides, right? That'll make this look like this. It's not going to make this look like this, okay? But generally, you know, you write down what you're trying to get to, and then you try to take what you know and turn it into at least some part of what you're trying to get to. So we can show the following. This is going to be equal to the thing we know that first part is equal to, plus the same thing, right? And now we certainly have c times some expression plus c times some other expression, and that's absolutely equal to c times that first expression plus that second expression. Because now we're factoring c out of simply two terms that are added together, each multiplied by c. So we can pull the c out of that, and now we've shown that this is equal to that. That's what we were trying to prove.
What's wrong with distributing the c? Isn't the same thing that was wrong with
What do you mean distributing the c?
distributing it through the
Where?
on the right both have an an plus 1 in them, unless I'm seeing that incorrectly. The proved part, right?
Right. So what do you want to do from here?
One step above.
Up here?
Yeah.
So we could distribute the c and say that this is c times right, we can do that. But we can't necessarily go from here to this, right? So we can show that, well, we don't know this. Okay, this is the problem. We haven't shown this yet. So we can't derive anything from that. Right, this is what we're trying to show. And we can show that this right-hand side is equal to this thing that I just mercilessly crossed out. It's equal to c times this plus c times that. And then we could say that this thing is equal to this, because that's what we were given. And so this thing plus this is equal to this plus this, and that'll show that this is equal to that. And it's really just working from the other side, but it's exactly the same thing as what we did here. But we still, all we're showing is that given that this holds for n variables, it also holds for n plus 1. But then we put that with a base case and we say mathematical induction, and now we've got it for all n. So it's in some ways, when you look at these things, they look silly, right? It seems like we're not really doing anything except maybe adding some more lines to the page. But really, we're doing something very powerful. Right, we're applying what we would do to go from, say, 3 terms to 4 terms, right? What we did over here, where we had this and we tried to get to, 4 terms, or we went from 2 to 3 here, but we're doing it in general, and then saying that since this implies that, we can actually conclude this is true for all n. So part A is the same idea, except you're doing a sum and breaking it up into 2 sums. Does that give you a start?
Yeah, it's just, I don't know, it's still confusing. My instinct would be to just distribute the c through and say they're the same.
So tell me where you'd like to distribute the c.
In the proof thing, you have an plus 1 there.
So, but we can't work with this, right? So here's the danger. Prove 1 equals 2. Well, let's multiply both sides by 0. 0 equals 0, that's true. 1 must equal 2. You can't work the proof in that direction, right? All we can show is that something that follows from this, right, means that if this is true, that thing that we derived is also true. If 1 equals true, then 0 equals 0. And that's still absolutely true. But we can't go in the other direction and say this thing that we derived is true, therefore the thing we started with is true. Right? Because then we could do this, 0 equals 0, therefore 1 equals 2. You have to start with the given, and you can do the same thing to both sides, and then that's also something that you know is true. And you can do arithmetic, and you can do, you know, a lot of things. And then if you can get from what you're given to this thing, right, then you can say this thing is true. It's a fairly subtle distinction, right, which way this proof is going. But it has a huge difference in terms of logical validity. All right, anything else? All right, well, we were doing mathematical induction yesterday on Towers of Hanoi. So remember we had 3 posts and we had n disks. And we had demonstrated that to move n disks from one post to another using the rules that were involved took 2 to the n minus 1 moves. And we know this is true for n equals 1 because to move one disk from one post to another takes 1 move, which is 2 to the 1 minus 1. 2 minus 1 is 1. So P of n is the proposition you can move n disks in 2 to the n minus 1 moves. We haven't shown that you need 2 to the n minus 1 moves. There could be a better way to do this. Okay, but what we've shown is that if you have 2 to the n minus 1 moves, that's sufficient to move n disks. So P of n is that proposition. P of 1 says you can move one disk in one move. 2 to the 1 minus 1 equals 1 move. And that's true. And so given P of n, and let's call our posts A, B, and C. So to move n plus 1 disks from A to B, here's what we can do. Move n disks from A to C, move largest disk from A to B, and then move the n disks again from C to B. So take most of the disks, put them over on C, put the biggest disk on B, and then take that majority of disks and put it back on B. And given P of n, we know that we can move these n disks in 2 to the n minus 1 moves. And we can move the largest disk in 1 move. And we can move those n disks back from C to B in 2 to the n minus 1. And so the total number of moves that are sufficient to do this is 2 to the n minus 1 plus 1 plus 2 to the n minus 1. And if you combine your terms, this will be 2 to the n plus 1 minus 1. And so P of n plus 1 is true. And so P of n is true for all n bigger than or equal to 1. And then we finished yesterday by eyeballing some code. And that takes advantage of this to actually solve Towers of Hanoi. So we ran through this yesterday, but let me just look at it a little more carefully here. So tower is the main function that will solve the problem for n disks. So the first argument is the number of disks you want to move, and the 3 posts are labeled 1, 2, and 3. So you tell tower which post you're starting from, which post you're moving to, and you also tell it what the number of the third post is, just so you don't have to calculate it. And then the tower function has a base case which says if you only have one disk, just move from the source post to the destination post. Otherwise, move num minus 1 disks from the source post to the open post, and then move 1 disk from, do that recursively, right, using your tower function, and then actually move 1 disk from the from post to the target post. That's the biggest one. And then call your tower function to move the num minus 1 disks from that open post to the destination post. And so this is the only time we actually make a move, when we move that largest disk, or in the case where we're only moving 1 disk at all. And the move routine just prints out the from and to post, and it prints out 5 of them per line. So let's do tower 8. And let's use an evil global to keep track of the total number of moves. So we'll just increment moves inside here. And when we're done with all of this, we'll just see how many moves it took. Let's see if AVG complains when I try to run this. Yep. I might deinstall AVG for that reason. I could abort it, but I'm kind of hoping it'll figure out eventually to let these things go. I'm hoping AVG is a little smaller footprint than Windows Defender. All right, so there's all the moves that it took, and it was a total of 255 moves, which is 2 to the 8th minus 1. So that's certainly what we were expecting. And if you play through those moves, actually moving the disks, right, it will do what it's supposed to. So how many times is the tower function called? Right, we call it once here in the main program, but every time we want to move a set of disks, it takes an extra 2 calls to the tower function. So let's put something in here. Instead of tracking the number of moves, let's track the number of calls to tower. Not this time. Abort. Oh, it's going to make me pay for that. Yeah. Or abort my whole laptop. Huh. There we go. Yeah. So the number of calls to the tower function was the same as the number of moves, 255. Which doesn't always happen, but it's kind of cool in this case. So if we want to run this on, the full supply of disks in the cave in Tibet, that's 64 disks, it's going to take 2 to the 64th minus 1 moves. How big is 2 to the 64th? Yeah, so 2 to the 10th is approximately 1,000. So you can build up from there, right, which is 10 to the third. So 2 to the 20th is 10 to the 6th. 2 to the 30th is 10 to the 9th. There's your gigabyte, right? So 2 to the 32 is 4 gig. 2 to the 40th is 10 to the 12th. 2 to the 50th is 10 to the 15th. 2 to the 60th is 10 to the 18th. And we got an extra 4, so it's 16 times 10 to the 18th, or 1.6 times 10 to the 19th. So big number. So there's 2 to the 64th. So I heard somebody talking yesterday, if you could move a disk in a millisecond, how long would it take to move all 64 disks? This is 1,000 disks per second, so these are really fast monks, lots of caffeine. So 2 to the 64th over 1,000 takes that many seconds. 3,600 seconds in an hour takes this many hours. 24 hours in a day, 365 days in a year, you're looking at 584,942,417 years. So a little over 500 million years to move the 64 disks. So our universe is safe for a while. And that's with 1,000 disks a second. Really cool SLP would build a robotic arm that'll like do this with some disks. Stick it in a display case. Yeah, yeah. I think it would be pretty cool. Yeah, you could sell it to the monks and they could outsource it to you. So what's happening with this recursion? So you want to solve the 8-disk Tower of Hanoi problem. And to do that, you need to solve a 7-disk problem, and then you need to solve a 7-disk problem. And to solve the 7-disk problem, you need to solve a 6-disk problem twice. And to solve this 7-disk problem, you need to solve a 6-disk problem twice. And to solve these, you just have to solve the 5-disk problem. But to do each of these, you need to do the same thing. And you can see where it's going, right? So at each level, we're doubling the number of times that we need to call our tower function. And at the last level, we're going to end up calling it 128 times. And then if you add up all of these, you're going to get 255. And so 64, right, our tree is 64 levels deep. You could, although this tower problem is a little different from this one because we're coming from a different set of posts. But you could do that, and in fact in 223, maybe actually in 222 we're going to do that. And that's going to be something called dynamic programming. And it's going to be a huge improvement on efficiency for a lot of recursive algorithms. So along those lines, let's just peek at one other classic case of recursion. So back to Fibonacci numbers. And remember, f of n is just the sum of the two previous Fibonacci numbers. And our two base cases, f of 1 is 1 and f of 2 is 1. So if you want to find f of 10, it's pretty straightforward. F of 3 is f of 2 plus f of 1, which is just the number 2. F of 4 is going to be f of 3 plus f of 2, so it's 2 plus 1 equals 3. F of 5 is just 3 plus 2, which is 5. F of 6 is 5 plus 3, which is 8, and you keep going. And you can make a while loop to do this, and it's very, very simple. You keep track of your two previous numbers. In your while loop, you simply add those together. That's your next Fibonacci number. And then you just adjust your two variables. So your previous number is the one you just computed, and the second previous number is the one that used to be the previous. So it's kind of like doing the pointers and lists, right? And you just go back to the top of the loop. And it takes you about 3 operations per loop. And so to find the 40th Fibonacci number, it takes you about 120 operations plus the overhead of a while. So it'll finish, in a few milliseconds. But we can also use this to write a recursive Fibonacci function as follows. So our Fibonacci function takes an integer n, and if n is less than or equal to 2, it returns 1. Those are our base cases. F of 1 equals 1, f of 2 equals 1. Otherwise, we calculate Fibonacci of n minus 1, Fibonacci of n minus 2. We add them together, and that's the return value. So it's a direct implementation of this recursive relation and the two base cases. And this main program will generate the first 1,000 Fibonacci numbers. So n just goes from 1 to 1,000. It'll calculate fib of n and then print out what the answer is. Let me guess. Ta-da. Let's try that. There we go. That's still doing it, though. This isn't the program actually running. It's thinking about it. There we go. So these first few Fibonacci numbers came out pretty quickly, right? 5, 8, 13, 21, and so on. But it's getting really slow. So it's working on 43 all this time. There's 43. And
real long load time, and be slow on the first one, start to speed back up again.
yeah.
So it doesn't have to like throw it out and then start coming backwards.
Yeah. So what's going on here? And this will never get to 50, right? It's slowing down so severely that I don't think it'll finish 50, at least not in the next 20 minutes. We got to start back from the top every time. So let's make one of these tree-like pictures. Suppose we want to find, let's say f of 6. All we've got to do is find f of 5 and f of 4, and then add them together. To find f of 5, we need to find f of 4 and f of 3. And to find f of 4, we need f of 3 and f of 2. And to find f of 3, we need f of 2 and f of 1. And f of 1 and f of 2, we don't have to call recursively because those were base cases. Those just return 1. So this will just return 1. F of 3 will need f of 2 and f of 1. And over here, f of 4 needs f of 3 and f of 2. And f of 3 needs f of 2 and f of 1. So we're doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 calls to our Fibonacci function to find f6. And if we look for f7, we're probably going to do 31 calls and 63, and it's going to be 2 to the n minus 1. It's actually n minus 2, but it's power of 2. So this is growing as badly as the Towers of Hanoi did. And in this case, we can use dynamic programming. The first time we calculate f3, we can save its value in an array. And now we want to find f3, we don't have to do these calls. We can just recall what f3 was from an array. And in fact, the first time we calculate f4, we can save that. We're not going to have to do any of these. And so we can speed this up and get it back to linear performance. That's coming later in 222. But here's a different version of the program. So I added a global variable here called level. and I initialized it to 0. And every time that we call Fibonacci, we increment level, and every time that we return from Fibonacci, we decrement level. So I want to see how deeply nested our calls to Fibonacci become. And each time we're inside Fibonacci, I'm going to print out the number that we passed to it, but I'm going to indent it by however many times we've called our function. And I've already compiled it, so AVG doesn't have to check it. So here's what's going on. Let me run this through more. So to find Fibonacci 3, first we had to call 2 and 1, and then we came up with our answer. To find F4, we had to find 3, and to find 3, we had to find 2 and 1, and then we had to find 2. Let's look at Fib 6. Oh, I missed it. All right, so this is the calculation of F6. So first it had to calculate F5, which meant it had to calculate F4, and then 3, and then 2, and then 1. So that was this set of calculations. And then after it found 1, it had to calculate 3 again. And to do that, it had to calculate 2 and 1. And that was, well, it did an F2. Then it had to do 3 and 2 and 1, and that was that branch. And then it had to go back and find F4. And to do that, it had to find 3 and 2 and 1, and then it had to find 2. So that's that 4, 3, 2, 1, and then F2. And so if you just let this thing run for a while. So here's the calculation of F16, and you can see it's getting fairly deep in the calls. And it gets all the way down to F1. It should be done at that point. But in fact, it's going to slowly pop back up and keep filling in the other parts of this tree. And it's going to do a lot of work.
Does this end up being fractal?
It might. We can like make it really, really small. See. But there might be something interesting going on in there.
Like goes out as far as it goes, and then it goes back. But when it goes back, it goes one more back.
Yeah, then it does almost as much work the next step. So recursion is interesting, okay, but it basically comes out of mathematical induction.
Finding all the small numbers, you can print them when you find them.
Mm-hmm.
But then it would print a lot more than you need. But
right.
You find the highest number faster.
True. So yeah, this idea of dynamic programming is a huge time saver. Right? So one way to do this is we're trying to find f of n, so we find f of n minus 1, f of n minus 2. We start marching down the tree, but we stave the stuff as we find it. So if we find f4 here, now when we need to find f4 here, we just use the value we saved. But a totally different approach is to just work from the beginning on up. Start with f of 1 is 1, f of 2 is 1, and calculate f of 3, it's just the sum of those. Calculate f of 4, it's just the sum of those, and there's no recursion suddenly. Right? And if we do this 100 times, we'll have f of 100. And it took 100 of these addition operations, basically. So very, very, very different orders of a complexity here, right? But in this case, for this particular algorithm, we can run it forward as easily or easier than running it backwards, but with a lot less work. All right, so that's pretty much all I want to say right now about mathematical induction and recursion. We'll talk a lot of recursion in 222. But that's a pretty good overview of mathematical induction. We'll be bumping into it for the rest of the next, 5.5 weeks, the rest of the term. Actually, it's only 4.5 weeks left. So it's going to be there, right? And we'll bump into it, and we'll encounter things that we might want to prove, and more often than not, the way we go about proving them is going to be mathematical induction, right? That's almost always going to be the right answer in here. But I don't want to spend any more time looking at that for now. I want to switch into our next topic. So our next subject is number theory. And number theory is literally the theory of numbers. It's the study of numbers, mostly the study of integers for what we're going to do, and largely just positive integers. So kind of the most simple mathematical objects we've encountered in our lives, 1, 2, 3, 4, 5, right? Whole numbers, positive. How much theory can there be about that? Well, it turns out there's a lot. Number theory is one of these areas where, because we're all familiar with numbers, we know about addition and multiplication and stuff, we can state problems in number theory in a way that's pretty easy to understand what the problem's asking. But a lot of these problems are phenomenally difficult to solve, and many of them have no known solution. So this is a huge area for so-called amateur mathematicians, hobbyists, people who are just kind of math geeks, right? I would one of these, who just like the stuff but haven't actually studied it or been trained in it, but can play around with this stuff because it's using things that we understand, right? It's one of the easier areas to work in without any formal training, and so it's spawned a number of interesting problems, and more than a few interesting areas of mathematics have come out of the study of number theory. Let me give you a couple of examples to start us off, and then we'll get into some formalism. Bless you. So Pythagorean triangle. And Pythagoras had this relationship that if we call this x and y, and we call the hypotenuse z, for any right triangle, x squared plus y squared equals z squared. And in this particular case, x is 3, y is 4, z turns out to be 5. 3 squared plus 4 squared, 9 plus 16 is 25. That's 5 squared. And the Pythagoreans were nuts about integers. They loved whole numbers. They loved integers, right? And so they were very interested in triangles where you could represent each side with a whole number. So this is a Pythagorean triangle. It's not just any right triangle. It's one where the lengths are all integers. So another one is 5, 12, and 13. 144 plus 25 is 169, which is 13 squared. So the question comes up, is there a way to sort of describe all the triangles where the sides are whole numbers? Is there a way to categorize those? And one way to get more triangles, if 3, 4, 5 is a Pythagorean triangle, so is 6, 8, 10. Because if you multiply each side by 2, then when you square it, you multiply by 4, and this just becomes 4x squared plus 4y squared equals 4z squared. So pretty quickly you realize that if you have even just one triangle, you have an infinite number of triangles with whole numbers describing the length of each side. But this triangle and this triangle are fundamentally different. This isn't just a multiple, a bigger version of this one, right? It's got a different ratio. So what are the different ratios that will give us this behavior? And the Greeks had some good answers to this. And you can find answers to this numerically. You can find it through number theory. You can find it through something called algebraic geometry, which is a very advanced field of mathematics. There's lots of different paths that will lead you to the solution to this question of what are the possible Pythagorean triangles. So that's a question that's been studied, and this is a particular example of something that's sometimes called a Diophantine equation, an equation you want to solve in integers. And the question of which equations you can solve has been interesting for a long time. So Fermat, how many people have heard of Fermat? He's been on Star Trek, so you should have heard of him. Fermat was a mathematician, 1700s, I believe. Don't quote me, could be 1800s. It's a few hundred years ago. And he was reading a book on Diophantine equations, and there was a section that talked about this particular equation. And he scribbled a note in the margin of his book. He wrote in his textbooks. He scribbled a note in the margin saying, this is very interesting, because while you can solve this equation, there are no integers which will solve this equation. X cubed plus y cubed equals z cubed, except for silly solutions like 0 cubed plus 0 cubed equals 0 cubed, or 2 cubed plus 0 cubed equals 2 cubed, right? Those are kind of non-solutions. But in general, there's no integers that satisfy this equation. And he scribbled this note in the margin, and he said, I've developed a marvelous proof for this, that this margin is too small to contain. And then, not too long after, he passed away. And while going through his effects, somebody found his copy of this book, and while flipping through it, found his note in the margin saying that he had a proof that there was no solution to this in integers. But there was no proof in the margin, because the margin was too small. So people started looking for a solution to this, and I think he actually claimed that he had a proof for the general case for any n bigger than or equal to 3. So you can't solve x to the fourth plus y to the fourth equals z to the fourth, or any other power bigger than 2. So people started looking for a proof to this theorem, and this was called Fermat's last theorem. And Fermat came up with a proof in his head. He was an extremely bright, talented mathematician, but he claimed to have come up with a proof in his head, so certainly somebody else could reproduce this proof, right? And people started trying to construct the proof of Fermat's last theorem, and nobody was able to. And it became an obsession, and it became a target of lots of amateur mathematicians and lots of trained, dedicated mathematicians. And it worked its way into folklore, and it's been in, stories and all kinds of things. And this problem eluded mathematicians for over a century. And it was demonstrated numerically for very large values of x, y, and z. And eventually people started to prove particular cases. If x, y, and z solve this, they have to have these very unique set of characteristics. And it's very unlikely that any numbers exist with those characteristics. But nobody had a definitive proof of this. And people would come up with things they thought were proofs, and they would publish these. And people would study the proofs and say, oh, you made an assumption here that's incorrect. And they would go back and they would try to fix their proof. And in some cases, in the process of trying to do this, new branches of mathematics were developed. So something called ideal theory came out of an attempt to fix a mistaken assumption that someone named Kummer had in trying to prove this theorem. And eventually, proofs were found for particular values of n. This case was proven. But for the general case of x to the n plus y to the n equals z to the n, nobody proved that until the 90s. And in the 90s, coming out of a field called algebraic geometry, somebody finally came up with a proof for this. His name was Andrew Weil, and it was groundbreaking. And the proof is way beyond the comprehension of most people. It's way, way beyond my comprehension. because it comes out of, you know, thousands or tens of thousands of other proofs that this was all built on top of in areas like algebraic geometry. But eventually it was shown to be true. And it's such a simple statement, right? Just find 3 integers so that the sum of the cubes of 2 of them equals the cube of the third, right? But it's so phenomenally difficult to prove that you can't do that. And it was finally proved in the 90s, and there was a big prize for it, and it kind of like was the big headlines in the mathematics world for a while. And it took months for people to validate that the proof was correct, right? But eventually it was validated, and everyone agreed, yes, this definitively proves Fermat's last theorem. So that's the fun side of number theory, right? Is that there's these problems we can understand, but sometimes they're pretty easy to solve. Sometimes they take you way off into like totally different directions, and you can lose yourself in there, which can be a good thing. All right, so tomorrow we're going to start talking about divisibility, what exactly we mean when we say that something is divisible by something else. And we'll come up with a definition of that will let us use it in proofs, and then we'll start talking about some proofs related to numbers, and we'll go on from there.